All right, so for this limit, um, usually if you see like a square root in the numerator, you're probably going to rationalize the numerator. But if you see one in the denominator, rationalizing the denominator really isn't going to help you very much. And you're still going to end up with 2x plus 1 minus 9 in the denominator if you rationalize that. And if you substitute 4 into that, you're going to get 9 minus 9. You're still back to getting 0. So that doesn't help you. So what we're going to do is a change of variable. We're going to let u equals that square root in the denominator, because we do want to get rid of that square root, 2x plus 1. All right, well, the limit is as x goes to 4. So as x goes to 4, in this square root, just sub in 4, you get 2 times 4, which is 8, plus 1 is 9. The square root of 9 is 3. So in this case, u will approach 3 as x approaches 4. All right, but we also need to know what x is. So let's rearrange this equation. We'll square both sides. So we get u squared equals 2x plus 1. Rearranging for x, we'll get u squared minus 1 equals 2x, or u squared minus 1 all over 2 equals x. So now we're going to sub in for u and x. So we get the limit as u approaches 3 of 4 minus x, which is u squared, minus 1 over 2, all over square root of 2x plus 1, which is u, minus 3. Okay, now if you still sub in your limit here, you realize you're still in trouble. So what we're going to do when you have a fraction in the numerator is we're going to just add it. So you can imagine the 4 as being 8 over 2. And so we can rewrite that then as the limit as u approaches 3 of 8 minus u squared minus 1 all over that 2, their common denominator, times by this u minus 3. All right, so now we can sort of factor the top there, but first I'm going to pull out, not factor, simplify, right? Because we have 8. There should be a, sorry, I should put a bracket here, just so we don't get confused with the negatives. Because we have 8 minus negative 1, which gives us 9. And then I'm also going to pull out a negative. So we get negative u squared minus 9 all over 2 times u minus 3. So that's a nice difference of squares, because the 9 is just 3 squared. So then we get the limit as u approaches 3 of negative u plus 3 and u minus 3. All over 2 times u minus 3. So those cancel. And now we can actually apply the limit and set u equals to 3. So we get minus 3 plus 3 all over 2, which is negative 6 over 2, or negative 3. For this question, we have a piecewise function, right, where we have the function equaling ax plus 3 when x is greater than 5. It equals 8 when x is 5. And it equals this quadratic when x is less than 5. And it says determine the values of a and b so that the function is continuous for all values. All right, so where are all these functions going to meet? They're going to meet or approach the same value when x is 5, right? This function approaches 5. This one is 5. And this one also approaches 5 from the other side. So what we want is, since this function has a value of 8 at 5, we want this function to also approach 8 when it reaches 5. And we want this function to also approach 8 when it reaches 5. So what we're going to do is we're going to take this and substitute x as 5. So a times 5 plus 3. And we're going to force that to be equal to 8. Because that's what we want it to approach. And this one as well, if we set x equal to 5, so we get 5 squared plus b times 5 plus a, right? We want that to also approach the value of 8 so that it's all continuous. So that's the setup of the problem. From here on in, you're just solving two equations for two unknowns. The first one actually only has one unknown, right? So you just have 5a equals 5, or a equals 1. And then once you have a equals 1, you can substitute that into your second equation. So we have 25 plus 5b plus a, which is 1, equals 8. Right? And then we can have 5b equal to 26. Bring it over, negative 26 plus 8 is minus 18. So b equals negative 18 over 5. So for this example, here's our function. Right? It's just a polynomial. And it says find the average rate of change. So finding the average is, again, finding the secant. Right? Or the slope of the secant, I should be more specific. Finding the slope of the secant. So the slope of the secant, which we'll just call m, right, is going to be the change in your y-coordinates, which is what the function equals at those values. So f at 3 minus f at negative 1. All over your x values, so 3 minus negative 1. Alright, so let's just go to the side and figure out what this function is at 3 and negative 1. So you just substitute 3, so you get 3 times 3 squared minus 7 times 3 plus 2. That gives you 8. And then finding the function at negative 1, 3 times negative 1 squared minus 7 times negative 1 plus 2 gives you 12. Alright, so we have 8 minus 12 all over 3 plus 1, which is 4. And that's just negative 4 over 4, so that's negative 1. So for the next one, finding the instantaneous rate of change at x at negative 1, we're going to find the limit of the difference quotient. So that means the limit as h approaches 0 for that function at negative 1 plus a little bit of h minus that function at negative 1, which we already know is 12, all over h. So we know what this function equals. So let's figure out what this one is. So f at negative 1 plus h. It's going to be 3 times negative 1 plus h all squared minus 7 negative 1 plus h plus 2. Alright, so expand that. We end up with 3, 1 plus h squared minus 2h plus 7 minus 7h, and we still got that plus 2 on the end. Alright, distribute the 3, so 3 plus 3h squared minus 6h minus 7h, and 7 plus 2 is 9. And just collect like terms. So we end up with 3h squared minus 13h plus 12. Okay, substitute this in. We get the limit as h approaches 0 of 3h squared minus 13h plus 12 minus the function at negative 1, which we found in part A, is 12. So 12 minus 12 is just going to cancel, all over h. And now we're just going to factor out in h. So we get the limit of h times 3h minus 13 all over h. So our h's go away. And as we substitute h equal to 0, we're just left with negative 13. Now, if you're ever unsure about this, you guys have an additional skill now, since we've done a little bit of chapter 2. Find the derivative, right? F prime at x just equals, okay, 6x minus 7. And then find f prime at x at negative 1. So f prime at negative 1 equals 6 times negative 1 minus 7, which equals minus 13. And we're done in 2 lines. Oh, isn't that wonderful? If we're trying to find the limit as x approaches negative 2. So we just observe on the graph. Here's negative 2 right there. And you can see both functions approach the same value. In this case, 3. All right, so the limit as x approaches negative 2 is 3. And if I do give you functions, you can actually substitute those values to see if it works. Okay, as x approaches 0, right, here's 0, right, and you can see the value of the function approaches the same value from both left and right, which is negative 1. So yes, that limit does exist, it's negative 1. Finally, as x approaches 1, which is right here, as we approach it from the left, we get a value of 0. As we approach from the right, we get a value of 2. So the left and right hand side limits don't agree. Therefore, the limit does not exist. Now, for something to be continuous, remember you needed 2 things to happen. You needed the limit to exist, and you needed the function to be defined at that point. And it had to be the same point, right? The limits and the function needs to be defined there must equal. So writing it out, you say the limit as x approaches some value a from the left of f at x must equal the function being defined at that point, which must also equal the limit as x approaches a from the right for f at x. All of that must be true. So in this case, at negative 2, right there, we know the limit exists. We've already analyzed that. And if you look at your function, I didn't write it on here. Let me just go grab it. So if you look at your function, you can see even though this one says x is greater than negative 2, this one says less than or equal to. So that means the function is defined at negative 2. So yes, it is continuous at negative 2. So I'm just going to write yes, continuous. All right, so just to recap, at x equals negative 2, it is continuous because the limit exists. It approaches the same value from the left and the right, and the function exists at that point. We know that because it says here less than or equal to. However, be careful, because if I change that to simply less than, this one is also just greater than, not equal to. So that means the function itself wouldn't be defined at that point. And so the function would not have a value at, say, negative 2. And so, no, it would not be continuous. So you have to be very careful whether or not there's an equal to there as well. Okay, and if you have the functions, right, you don't have to look at the graph to determine their limits. Right, you can just test left side and right side limits and see if they're equal to each other. So in this case, where x approaches 1, you can clearly see on the graph. But if you didn't have a graph, right, if you're approaching 1 from the left, that means you're approaching from a value less than 1, which due to this domain is this function here. So if you sub in x equals to 1 in that function, you get 1 squared minus 1, which is 0. And you can see that on the graph. And then you approach 1 from the right, which would be this function, because you're approaching from values greater than 1. So if you sub 1 into here, you get minus 2 times 1, which is minus 2, plus 4, which is 2, which you can see on the graphs. So those values do not equal each other. So the limit does not exist. And because the limit does not exist, it is not continuous.